All right, well, welcome to lecture 13 in general relativity. At last, I'm back to it. I think I've recovered from my grading. Anyway, here we go. So I just wanted to give a quick sort of just overview lecture following the first section in chapter 3 in Carroll. Not exactly, but just to try to give an overview of what we're about to do because it's pretty technical and it's going to take a little bit of work, I think. But the big idea is here, what is curvature, and how do we exactly calculate curvature? What is curvature anyway? So I think the first thing that I should mention, because at least some of you have previously studied elementary differential geometry, I'm thinking in particular the text by Barrett O'Neill, and you may recall for a surface, right, which was a two-dimensional manifold, that we could calculate a scalar which was known as the Gaussian curvature. And furthermore, when that Gaussian curvature, which I think we used a big K for, if that is equal to 0, well then the surface is called flat, right? So for example, if you have this surface here, even though extrinsically speaking, right, you can see that it's curved, right? But the thing is, you know, um, from this perspective of Gaussian curvature, this would be a flat surface, right? So any surface that you can form by like smoothly rolling a sheet, it's like a cone away from its singular point, would be flat as well. And the idea there is that if you were somehow a two-dimensional being, right, and you were living in that surface, and you did experiments, you wouldn't be able to detect any real distinction between your surface and just the plane. In that sense, it's flat. Of course, if you were living in a cylinder and you kept walking in one direction and got back where you started, well then you'd know something was up, right? But that wouldn't be the kind of departure from Euclidean geometry would be looking for with the curvature. Curvature is a local notion. So whatever's going on with curvature, it's got to be something that's like locally defined. It's not something about the global topology, let's say, of the surface. Although there are connections, right? Because you may recall that the Gauss-Bonnet theorem linked curvature to the Euler characteristic of the surface, and you might recall that the proof that we went through involved studying how tangent vectors bend around corners, and that those angle I forget what they're called, defects or whatever. I would say that that's a foreshadowing for what we'll study in the more general context, namely like parallel transport of a vector. That ties into the discussion of curvature as well, because there were, well, it will. So these circle of ideas, they're all linked. But anyway, I don't want to get too technical here, but just to say that there are things you can see from the surface study that sort of are giving you some sense of what we're about to do, but not exactly though. See, because before everything we did was two-dimensional, but now we're trying to generalize that concept of curvature to higher dimensional manifolds. And so again, I'm mostly following Carroll, whose approach is approximately the same as I saw in my general relativity course at SUNY Stony Brook a few years ago. But well, that's not quite honest. The course I had at Stony Brook, we used the tetrad formalism, and it was a way of doing general relativity with differential forms, really kind of more in the spirit, in some sense, of O'Neill. We won't be doing that, at least not to start with in here. We're going to follow the sort of traditional metric-based approach. So let's just take a little tour ahead of the equations which we're trying to, and the objects we're trying to understand, and see what these objects are and why do we need to look at them, I'm not really going to answer that in there. I'll answer that at a somewhat fluffy level in this lecture, okay? So one of the first things we'll have to motivate is the introduction of this thing called the Christoffel symbol. So the Christoffel symbol is defined as it's given right here. I mean, this is the definition of the Christoffel symbol. It's this particular combination of first derivatives of the metric contracted over the inverse metric, which is, you know, kind of a mysterious formula. It's not a tensor. However, you can use it to make derivatives into tensors. All right, so that's one of the, I think that's pretty much how the Christoffel symbol was introduced to me in my general relativity courses. Like, if you want to take a vector and make it into a genuine vector, well, not the vector. If you want to take a vector, right, a given vector on a space, and you want to make its derivative, if you want to make its derivative also a vector, well, then you need to introduce these compensating terms, the so-called Christoffel symbols, and by contracting the vector against the Christoffel symbols like such, it will make the covariant derivative of a vector once more a vector. So, you know, those are just claims at the moment, but it turns out that if you define the Christoffel symbol like such, then, you know, that will make this, the covariant derivative of a vector, again an honest to goodness vector. And it's not just that. You can also talk about covariant derivatives of other tensors by suitably adding terms involving the Christoffel symbols. Talk about the covariant derivative of any rank, well, any type tensor you want. Okay, so I should also say this, I suppose. In the case that your metric is constant, right? If your metric was constant, then these formulas are really boring because that's zero, that's it's all zero, you know, if the metric is constant over your space. So for a constant metric space, this all drops just to zero, and the covariant derivative is just the ordinary derivative, right? So that's a lot of the reason we wouldn't need these. We've never seen these things before this context, right? Because we've always been working in a space where the Christoffel symbols were trivial, or, well, although sometimes we work in a space where the Christoffel symbols are trivial with respect to one coordinate system, but if you choose a curved coordinate system, you might nevertheless introduce non-trivial Christoffel symbols in. So you experienced a little bit of that technology in Calculus 3 if you think back to, if you've seen the formulas for divergence, curl, and such in nonlinear coordinate systems. That's a place where, even though your space, I think, is intrinsically flat, R3, you're using coordinates which nevertheless have non-trivial Christoffel symbols. Okay, anyway, let's see here. I hope what I said was true. I'm about 90% on it. Sorry, guys. Let's go on here. Yeah, you can let me know in the comments if I'm incorrect, right? Maybe my future self will leave a comment here. I don't know. We'll find out. But once you have this covariant derivative of vectors, then if you apply this to the context of a like a velocity vector, I think you end up with this down here, or maybe the acceleration. I'm trying to remember. Well, we will derive it soon enough, but this is the geodesic equation. This is the equation for a generalized line in our space, and as you can see, it involves these Christoffel symbols, right? So now if the Christoffel symbol is 0, well, that's easy. Then you just get the second derivative of the position with respect to your parameter for the path is equal to 0, and you just integrate twice, and you've got, you know, the solution is, well, I guess I can write it here, right? I'll use brown. So like, if, you know, if gamma, the Christoffel symbol here, capital gamma, right? If these guys are equal to 0, then you just get d squared x mu d lambda squared equal to 0, right? So if we integrate twice, we get x mu as a function of lambda is just equal to some constant vector a mu plus lambda b mu, you know. And So that's just a plain old garden variety line. So the geodesics, when your Christoffel symbols are 0, are just lines, but more generally they can be more interesting things, right? Like great circles on a sphere, you could derive that. Once we have, done the groundwork for that, and I think most of those things are in Carroll, so we'll hopefully go through them. And then once you have, now I have not explained why that's the geodesic equation, but it is, it's a natural, it's just what happens when you write the equation for acceleration being 0 in the generalized sense of acceleration. So that has to go through the covariant derivative idea and so forth. I think it's the, I'll probably get into trouble here, but it's, well, okay, let me not. I was trying not to do that, so we'll get back to it. We'll derive it, okay? So here, this is then the next step in the game is to introduce the Riemann curvature tensor. All right. Obviously, there's not a lot of like at this level of the conversation. Like, how do you get from here to here? Who knows? It's not at all obvious. In fact, the way this is derived is, well, I suppose there's a few different ways to do it, but I think Carroll looks at like a commutator of vector fields and does some things with that, and out pops this term as a sort of signature of vector fields not commuting. So this curvature is an obstruction to flatness in some sense. And anyway, here it is. So it's defined as the curvature is defined as terms of derivatives of the Christoffel symbols, as well as contracted. This is a sum of the Christoffel symbols against itself, suitably anti-symmetrized, I suppose here. See, because you've got mu sigma, and then well, yeah. So mu here. Let's see here, mu here, nu here. Nu here, mu here. I think this has been anti-symmetrized in. Yeah, this is anti-symmetric in mu and nu. If you look at this overall, this expression has an anti-symmetry in the indices mu and nu. But hey, let's not get ahead of it. There's like a whole section on the symmetry properties of the Riemann curvature tensor and Carroll, of which they're not trivial. It takes some time to really digest them. But there it is. This is the Riemann curvature tensor. Somehow hidden in this thing is the Gaussian curvature. Now, in the right context and interpretation, right? Now, I don't think Carroll talks about sectional curvatures, but you can talk about sectional curvatures, and there you actually look at kind of like slices of your manifold, and you look at the curvature of the slice, and there you kind of have something more directly touching back to the Gaussian curvature. I want to say the book, I'm remembering Burns and Gidea, but it's been a few years since I worked through that with a student. So anyway, let's continue on here. And so here we're leaving Carroll's chapter 3. I'm actually going ahead to chapter 4 because I figured, as long as we're not deriving things, let's just kind of give a view ahead to the end of the story here. And so like the next thing you do past the curvature tensor is construct the Ricci tensor, which you take the curvature Riemann tensor, which is a type 1 3 tensor rather, and you contract the upper index and the middle lower index like that, and that leaves you with a 0 2 tensor, r mu nu, which is of the same type as like the metric, right? Type 0 2 tensor, and then you can contract it further. So you can raise one of these indices and contract it against the other to get a genuine scalar. And so the scalar here's the formula in terms of the Ricci tensor, g mu nu, r mu nu, and this is a sum over mu and nu. Everything, all repeated index are summed in this lecture. We're back to that again, okay? And so once you have those, then it's interesting that physics requires you to introduce yet another tensor, which is built in a kind of funny way. So you take the Ricci tensor and subtract 1/2 the Ricci scalar times the metric tensor, and this defines what's called the Einstein tensor. And the reason, so you can kind of understand why it took Einstein a few years to find the equations that I'm about to write here, because it's a little quirky, you know. It's not quite exactly just something. It's not just what the mathematicians already did and set it equal to something like, you know, Newtonian mechanics. You take ma, set it equal to f, right? So like, if you had mathematicians playing around with acceleration already, it was kind of okay. Well then, I mean, okay, in due respect to Newton, he did kind of invent acceleration in some sense, in the technical sense. So I guess it's not a very relevant point. But my point to you is that I think if Einstein had went and opened up math books written by, say, Relativity and the other forefathers of tensor calculus, I don't think he would have found the Einstein tensor just sitting there to use. I think this is something Einstein had to kind of build from base principles in order to find the right. It took some time to write these equations down, okay? And I think you can kind of appreciate why, because it's some sort of admixture of the sort of the more natural objects from the math point of view, the Ricci tensor and the Ricci scalar. But these are Einstein Field Equations, and they say that the Einstein tensor is equal to 8 pi g. G is the universal gravitational constant. You remember that thing? I haven't taught physics recently enough to know the number, but it's tiny, right? And then this right here, the T mu nu is what? Here, T mu nu is the stress energy tensor. I can't spell energy tensor. So the stress energy tensor has, various forms depending on your context. Like, for example, the stress energy tensor is it's 0 in the vacuum of space, right? And it's like if your stress well, I guess then that question drags us up into a more larger cosmological discussion. But setting aside those issues for a second, like the cosmological constant and all that jazz. If you had stress energy tensor 0, then the Einstein equations, if you contract them and look at them, you just end up with, like, if this is 0, it ends up making the Ricci scalar 0. So like, if you're in the absence of mass and energy, your space is flat. So again, if the Ricci scalar is 0, that gives you flat space. Anyway, yeah, these are Einstein Field Equations. This is sort of the analog of Maxwell's equations, but for general relativity. And we will see how to solve these in particular contexts as we go on. And Carroll, like I think pretty well discusses like how to solve them in the what was that thing called? The maximally symmetric case. And then there's a whole chapter on the Schwarzschild solution and other things. So we'd like to understand, our goal, right, is ultimately to understand how these Einstein field equations reproduce in some limiting sense, right, the equations that we know and love from Newtonian relativity. Because somehow or another, this, in the proper interpretation, will circle back to Newtonian gravity. I don't think it's at all obvious why that is. And it takes, you have to be patient, right? It's going to take some time to really explain that. The course I took in general relativity, actually, at NC State, one of our final exam problems actually was essentially to just do that, to like show how the Einstein field equations reproduce, 9.8 meters per second squared, if you put in all the relevant assumptions and specializations and so forth. And it took me a while to really flesh it out. And even that was, of course, with assumptions like the Earth is a perfect sphere of an ideal gas or some silliness like that and things like that. But anyway, this is where we're going. And sorry, I'm obviously behind schedule here, but I'm trying to continue on here. So anyway, that's all I got for today, but thanks guys. Talk to you soon.